With patterns, equations, and graphs, this is where you're going to see 3 different languages of algebra fit together as one. You can take one math sentence, one equation, you can represent it as a pattern, as the equation, where it's something like 3 plus x equals y, and then the graph for it. So the target is I can use tables, equations, and graphs to describe different relationships. Remember last lesson we looked at the solution of an equation with one variable. Here we're having 2 variables. So solution of equation with 2 variables, x and y, is any ordered pair. So think graphs. The x shows you left to right where to go on that coordinate plane. The y value shows up and down how far to go on that coordinate plane. So it's 2 variables. You have that ordered pair, and what it does is it makes that equation true. It means when you substitute those values into the equation, each side has the same value. So something like the coordinate 520 is a solution to the equation y equals 4x, because when I put those values in there, when I put 20 in for y, as you see here, and when I put 5 in for the x here, they equal out because 4 times 5 is 20. Therefore, the solution to this equation, because it has 2 variables, is 520. This is going to be a shift for you because you're not used to there being 2 numbers as part of the solution. Here is a table that's going to organize equation, table, and graph. You need 3 columns and 2 rows. So across the top you have the equation. That's one language of it. The second language is going to be the table, and the third language is the graph. So let's take the equation. We're going to use the same equation and communicate it with a table and with a graph. And we'll be looking at the graphing calculator how to see these work interchangeably. You have d equals negative 50 times m. So what this does, the equation shows how the variables are related. I take the m, which would be like the x value, I multiply it by negative 50, and that tells me what d is. M is the independent variable. The independent variable is always the x. D is always the dependent variable. I can't know what D is until somebody tells me what M is. Now this could also be something like in real life, like minutes and how far you go as far as distance. Now here's the table. You've seen one of these before. You might have heard it described as a function table. So M, the independent variable, D, the dependent variable. The table identifies the values that make the function true. There are infinitely many solutions that I can put into this equation. We're starting with 0. We're doing 0, 1, 2, 3, 4. I could have put in negative 2. I could have put in negative 200. I could have put in positive 265 and put that in there and still have gotten a D value. So in the middle here, I've taken the M value, put it into this function, negative 50. So negative 50 times 0 is 0. So that's my D value. Again, 1 times negative 50 is negative 50, 2 times negative 50 is negative 100, and so forth. What this function table does is it organizes ordered pairs for me. The x value is the independent variable, which is what's represented with M, and the y value is the dependent variable. There you go. And I create a graph. So I have these ordered pairs graphed. 0, 0 is right here. 1, negative 50, 1, negative 50. 2, negative 100, 2, negative 100, 3, negative 150, so 1, 2, 3, down 1, 2, 3, there we go. 4, negative 200, so to the right 4 because it's positive, and down to negative 200. And notice that it's going on. I have an arrow going that way because it would go on and on and on. The graph is the visual image of the values in the variable. In this case, the graph is continuous, so draw a line through all the points. And depending on the real life situation that goes with it, it may continue one way and not the other way. But in a general case, if there's no real life situation attached to it, it would extend in both directions. And so this is taken from an example where it is a real life situation, but I spared you of that part. You want to connect the dots and you want to draw the arrows with them. So you've seen when you have an equation with 2 variables, an x and a y, the solution is no longer one number. It's no longer x equals 4. It's going to be an ordered pair, such as 4, 1. So when you're checking to see if it is a solution to that equation, you're doing that the same way as you did before with a 1 variable equation. You're going to take that ordered pair, substitute it in, and see if it balances out, if both sides of the equal sign are equal. So x is the 4, so that's going to go in for x. 1 is the y value, so let's plug those values in. 1 equals -4 plus 3. So simplify that down. 1 equals -4 plus 3 is -1. 1 does not equal -1, therefore no, 1 is not a solution to that equation. Let's come over here to practice B. Y equals x plus 2/3, and our possible solution is 1/3. 1 is the x value, so it's going to go in right here. 1/3 is the y value. If you get your x's and your y's mixed up, I would suggest putting in the corner of your paper x, y, so you remember that the first one is the x value, and circling and pointing to it as you rewrite the problem so you get the right part of the ordered pair and the right part of the equation. So let's plug this in. 1/3 equals 1 plus 2/3. Okay, so let's simplify this down. Does 1/3 equal 1 2/3? Well, of course it doesn't. So no, that is not a solution. Here we need to represent the situation with a table, with an equation, and with a graph. All three of those fit together, the table, the equation, and the graph. It's just kind of like different languages to communicate one idea. So the situation is Ty is 3 years younger than Bria. Let's do some translating. So we're going to make Ty. We don't know Ty's age, so we're going to make it T. Is would be the equal sign. 3 years younger than Bria. So younger than, it's like it's less than. Think of it in years. So he is 3 years. Think of that as less. And what do you know about the phrase less than? It switches the order. So it's going to be Bria minus 3. So let's piece that together. T equals Bria minus 3. Put some real life with it. In the absence of numbers, make up some numbers. So let's say Ty is 10 years old. If he's 3 years younger than Bria, that means Bria has to be 13. Make sense? So 13 minus 3 does equal 10. So that would work. So here's my equation. Now let's make a table. So Bria would be like we'll make it like your x value. So Bria, then you have your equation, Ty. Okay. B minus 3. So if Bria is, let's say, 8 years old, 8 minus 3 is 5. So an ordered pair for that would be 8, 5. Okay, let's say Bria is 7 years old. 7 minus 3 is 4. So Bria would be 7, Ty would be 4. I want to get one more point on there at least. 6 minus 3 is 3. And just for good measure, we're going to do another one. Let's do 5. Extend my table out. Hopefully yours will be prettier because you've got notebook paper and you're able to turn your paper. It's kind of hard to write horizontally on here. So now I have a table of possible solutions. This could be infinite. Nobody said that these were young children. These could be really old people. These could be 100-year-old. And so if Bria was 100, then Ty would be 97. It could go on and on and on. Now when we make our graph, we have to think about what is logical with this. Are you going to have negatives? Well, of course not. You're not going to have negative years. So I only need quadrant 1 of my graph. Bria is like the x value. So Bria is going to go down here. Ty is going to be over here. I'm going to do like a little break here because I'm going to skip ahead to 5 years old. Make your increments even. Okay, so if Bria was 6, Bria was 5, then Ty would be 2. So we'll put, not 2, 3. My apologies. Okay. Actually, it should be 2. I wrote it wrong there. Okay, now we got it on track. I caught my own error. I'm going to make that 1-year-old just so it's even. 2, 3, 4, 5, 6. So if Bria is 5, Ty is 2 years old. So I'm putting that coordinate there. If Bria is 6, Ty is 3 years old. If Bria is 7, Ty is 4. If Bria is 8. Ty is 5. If Bria is 9, he's 6. And we didn't even have 10 on here. But what I can start to see is it is linear. It would go on and on and on. Now, I'm not putting an arrow in the other direction because it does not extend infinitely lower because, like we said, you wouldn't have negatives as ages. So you see the relationship. We have the equation, we have the table, and we have the graph.